Okay, so we are very happy today to have Damien Tageddine. So he has completed his PhD thesis at McGill University in 2024 and has been collaborating with Masoud Kalkali in Western Ontario since 2023. His main research interest is on non-commutative geometry. Specifically, his work focuses on spaces closely tied to discrete structures such as discrete group, tree, R-tree, graph, etc. Damien, please.
Thank you, Sebastian. Thank you for the kind introduction. And also thank you for the invitation to talk to this seminar. It's a great pleasure for me to be here. The title of this talk is Non-Commutative Geometry on PGL2CP and KMS states. In fact, I could have called this talk Non-Commutative Geometry on the Berkovich projective line, depending on your approach to the topics. You may think that the Berkovich line is the main character of the story, or you may think that PGL2CP is in fact the main character. I tend to think that PGL2CP is the main element here in this story. But anyway, so this is a joint work with Masoud Kalkali. It's actually a work in progress. We published one paper already on this subject, and probably at least two more on it will follow. So I start with this talk with at least the 15 to 20 minutes of this talk will be to try to give you the main ideas of what is the Berkovich space, what is the p-adic complex numbers, and try to give you a sort of intuitive approach to the subject. Why does it matter and how is it used in number theory, but also in operator algebra and so on. If I had to summarize the main idea of this Berkovich projective line, it would be the p-adic counterpart of what is done in algebraic geometry when one, study an algebraic structure and tries to take its analytification and study the analytic structure that is attached to it. Sort of a Gaga correspondence here. Here in the Berkovich projective line would play the p-adic counterpart to the complex plane in the classical structure. And one can think there is a Gaga correspondence as well in this p-adic work. Okay, so it has a fundamental importance in arithmetic and in number theory, and in many ways it is a more interesting space to study than CP for reasons that I'm going to explain. So let's start with a brief introduction about p-adic numbers. So a p-adic valuation of an integer is given by this map VP, which is given by the max of the n for Pn dividing the element A. If A is not 0, and if A is equal to 0, then we say that its valuation is equal to infinity. And now this valuation can be extended to rational numbers as follows. So you declare that the valuation of x is equal to p to the power minus vp. Sorry, this defines not a valuation, but an absolute value on rational, which is given by this. And for instance, the absolute value of an integer is going to be less or equal than 1, and then the absolute value of a rational of s is just p to the power vp of r minus vp of s. So this defines a p-adic absolute value, and it's in fact a non-Archimedean absolute value on Q. Okay, so here we are really entering the non-Archimedean world, and many of the structures that we are going to see in this talk are actually non-Archimedean counterpart of Archimedean structure that exists always. Okay, so what is a non-Archimedean metric on a field K? Essentially, the point 1 and 2 are the usual requirement for a metric, and really the important point is the third one, where we have instead of having the classical triangle inequality, we have this so-called ultrametric triangle inequality. So the absolute value of x plus y is less or equal than the maximum of the absolute value of x and the absolute value of y. Okay, and these have many fundamental geometric implication. The one of the striking one is that if you consider a ball in this metric, then every point inside this ball can be its center. So if x minus y is less or equal than r, then x and y can be both chosen to be the center of the ball. Another striking point, which is also very important in the definition of the Berkovich space, is that if you have a non-empty intersection of two p-adic balls, then either one is contained in the other. Yes, it should be an inclusion here. Yes.
Can you try to put full screen? Because we.
Oh, yes, of course. Sorry. Is it on full screen now?
Yeah. Better. Thank you.
Okay. Thank you. Okay. So now, what is a p-adic complex number? Well, a p-adic first, a p-adic rational number QP is the completion of Q with respect to this p-adic absolute value. And an element of Q can be written as a power series. So this summation over Z of AN PN, where AN is an element of the field FP, so the finite field, FP. And now, of course, QP is not algebraically closed, so you can take its algebraic closure, which I denote here by QP bar, and then the absolute value extends uniquely to this closure. And yet, this is not done yet, so this algebraic closure is not complete with respect to this absolute value, so you can take its completion, and you get the field CP, which is the field of p-adic complex number, and it's unique up to isomorphism. So an element in this field can be written as this summation, AN-PN, where now AN is an element of the algebraic closure of FP, which is now an infinite set compared to FP. And also, main thing is that CP is not locally compact. Okay, so that gives us a lot of challenge if one wants to work on CP, because CP is not that well behaved. As I said, it's not locally compact. It's in fact totally disconnected. So if one wants to do if we think in terms of analogy, if one wants to do complex analysis, but in the p-adic world, then there is a lot of difficulty because of this structure of CP. So we are tempted to look for a space that is close to CP in the idea, still p-adic, but with better topological properties. And in fact, the space that satisfies these properties is in fact the Berkovich analytic space. Before talking about that, yes?
Let me ask a question. Can you slide?
Yes, of course.
Yeah, so QP is like a number where you can have infinitely many decimal after the comma, but also before the comma on the left and the right.
Yes.
It's all the possible sequence are working. I mean, you can. There is no restriction.
Yes, I think yes. So you could take any series that is of this form, ANPN.
Okay, thank you.
Okay. So before talking about Berkovich space, maybe some comparison between QP and CP, and some I'm going to recall some definitions. So the valuation group is the image of so the invertible elements of your field under the valuation, so VP. In the case of QP, it is Z, and in the case of CP, it is the rational. So you see already from the point of view of this valuation group, the arithmetic is not too far, right? You get Z on one hand and Q on the other hand. The valuation ring is the set of elements in the field that have an absolute value that is less or equal than 1. It is also sometimes called the integer, the ring of integers. In the case of QP, it is ZP, and in the case of CP, well, here we're going to call it OCP. We have a unit group, which are the elements that have absolute value equal to 1. And the residue field, well, in the case of QP, it is FP, which is finite. And in the case of CP, it is the algebraic closure of FP, which is infinite. Okay, and that is also something that is very important. If one knows about the Bois-Titz tree, in the case of QP, it is going to be finite, locally finite tree because FP is finite. And in fact, the Berkovich space is not going to be locally finite because the closure of FP is not finite. So here the residue field, the cardinality of the residue field plays an important role in this story as well. Okay, so now let's dive into the Berkovich projective line. So what is the Berkovich projective line? Again, I'm going to talk about this analogy between the complex, which is something that we really understand, really know, and then I'll try to make the parallel with the case of CP. So if you want to, we can do a very trivial, maybe a bit stupid exercise, is that, okay, how can we visualize C? Of course, I mean, this has a trivial answer. It's the usual complex plane. But suppose you don't know what the complex plane is, but somehow you know what the Gelfand transform is. It's a duality that also allows you to describe C using its multiplicative seminorm. So to any multiplicative seminorms on actually functions over C, you can attach a complex number, which is the valuation of functions on that number. And in fact, you can restrict yourself to polynomials functions with coefficients in C. And because polynomials are dense and separate points, it's enough to understand and to recover C as a field. Okay, so all the seminorms are in fact evaluation at point evaluations. So you can recover the space as this map, which is the Gelfand transform. Now this is convenient when you pass to the complex p-adic case, because if I ask you the same question, but in the complex p-adic case, how to visualize CP, now it's a whole other story, right? I mean, you could see it from, and I guess this is the usual way people understand CP, is that you could see it as a space of power series, right? Over this algebraic closure. And I mean, from an algebraic perspective, this is enough, right, to understand CP. But if you want to introduce more geometry, have a geometric picture of what CP is, then what you could do is, again, see it through this Gelfand transform. So how do you do that? Well, you look at all the multiplicative seminorms over the field, over the polynomial rings with coefficients in CP. Now, the main difference is that, well, in the case of the classical complex space, we only had evaluations at a point. Now, the miracle in the non-Archimedean world is that you have much more multiplicative seminorm. If you consider a ball in this p-adic world, you can associate a seminorm to any ball centered at a point A. So A here is in CP, right? It's a complex p-adic number. R is a radius, so it's a real number. And you can associate a seminorm, which is the supremum of Fz. Fz is thought as a polynomial with coefficient in CP. And the miracle is that this thing here is also multiplicative. And you have an order that you can give to these seminorms because they are attached to balls. You can say that one seminorm is going to be less than another one if you have an inclusion of the two balls, if and only if. And so you see from here that, in fact, CP seen as this Gelfand transform, has a lot of geometric structure, right? You have relation of order between its points, and in fact, you can build a space out of this relation of order. First of all, we're going to call the Berkovich affine line the set of all multiplicative seminorms that I've just defined on CPX, so the ring of polynomials. I can then define the projective line, which is the one-point compactification of this affine line, and I can define the hyperbolic line, which is the interior of this projective line. And I give them the Gelfand topology, okay? And now all these spaces, this is why Berkovich, the Berkovich analytification is so interesting, is that all these spaces are path-connected, Hausdorff, and metric spaces, okay? And if you compare to CP, and also there are, well, P1CP is compact, so it's one-point compactification. So you can add this to the picture. And if you compare to CP, CP is certainly, yes.
I have a question. Is normal that you didn't include the points of type 4 in your definition of the Berkovich affine line?
They are included, yes. So I should, yeah, maybe I should be careful about this, saying that. I'm going to talk about the classification of points. So the type 4 points, which I'm going to say it in a few minutes, correspond to degenerate points. In fact, if you take, it is true that the Berkovich space is going to be so path-connected Hausdorff and metric space, but it's not spherically complete, which is to say that if you take inclusion of balls, okay, this gives you a sequence of points in this Berkovich space, but the intersection might be empty. And so in order to have a complete picture, you add this point, which is associated to this intersection. And this is going to be a type 4 point, which is thought as a degenerate point. But yes, that's also an important. But I'm going to mention that in a few seconds. Does this answer your question?
Yes.
Another important thing about this, the point of these spaces is that they have a diameter. So I told you that any points can be associated to a ball, and so you can say that the diameter of this point is equal to the radius, which is also the infimum of the norm of the affine polynomial t minus a when a ranges in CP. Okay, so we have, as I just mentioned, following up this question, so you have a classification of these points, and this classification relies on the diameters of these points. In fact, not really the diameters, but you can see any points as a sequence of balls, and you can look at the limits of this sequence, and then depending on the limits, then you have one type or the other. So type 1 points are types for which the diameter is going to be equal to 0, and they are in one-to-one correspondence with the classical projective space over CP, which is CP compactified, okay? The type 2 points are points for which the diameter is p to the power q, okay? So if you take the log p of this diameter, it's a rational point. It's a rational number. Hence, type 2 points are called irrational points. The type 3 points are the irrational points. So the diameter is not an element of this of the valuation ring. And the type 4 points are degenerate ending points, okay, which correspond, as I said, as this empty inclusion, sequence of inclusions of balls. And then to add to this picture, this affine line, it has a rooted R3 structure. So what is an R3? R3 is a sort of a generalization of a tree, where now, which makes it look like more of a continuous space, more than a discrete one in the sense of trees. And it's rooted, and the root is a type 2 points, which is called the Gauss point, and it's also denoted zeta Gauss. It corresponds to the balls centered at 0 with radius 1. Now I could explain, more what is a real tree, but I think a picture is better than many explanations here. So this is a picture of P1 CP. So as I told you, CP is completely disconnected, but the Berkovich identification of CP looks like this, which has a lot of resemblance to classical continuous space, and is very well suited when one is trying to do p-adic analysis. So look at this. Here in this space, so the interior points, you have the type 2 points and the type 3 points. The type 2 points are the branching of this tree. Okay, and now at each branching point, you have infinitely many branches, and every one of these branch is in one-to-one correspondence with an element of the closure of FP, the finite field. So remember, I told you that this closure is infinite, and so this tree, if you look at locally, okay, and you compare it to the Bourati's tree, so locally, instead of having finitely many branches, you have infinitely many. Okay, and this is in the case of CP. Still, the number of branches is countable. Okay, but you could imagine a wilder field, a non-Archimedean field, for which you would have uncountably many branches. Okay, so the picture is fairly. I mean, you have a lot of structures, right? Not trivial structure in this case. So the branching points are the type 2 ones. The type 3 points are the points in between the branching. Okay, so essentially they look like locally like lines. Okay, in between these branching points. The type 1 points are the points on the boundary. Okay, and the type 4 points are points where the branches ends before reaching infinity. Okay, and they are degenerate points. Okay, and yeah, so this Berkovich space is as I said, is well suited because of this tree structure, and there's a lot to say about this tree, because we know. I mean, you can already anticipate what I'm going to do is I'm going to study groups acting on this real tree, and then you'll get the full story. Okay. Yes.
Regarding the tree, can you go back to the previous slide?
Oh, yes, of course.
Is it a faithful representation of the Berkovich line, or it's just a picture?
I mean, yes, no, it's a picture. Of course, here, I mean, to represent it faithfully, you would have to be able to represent infinitely many branches. Something I didn't say, the type 2 points are dense. Okay, so of course, I mean, I cannot represent this clearly, but yes, you're correct. This is just to give you an idea. So it looks like a. I mean, at every type 2 points, you have infinitely many points. So it's like it has a sort of fractal structure, right? At each of these type 2 points, you have infinitely branchings, and you have a dense number of type 2 points, which, I mean, when you look at this, it has a crazy structure, okay? And somehow we are able to say a lot of things regarding this Berkovich space. Does this answer your question?
So, I mean, this is just you can partition the Berkovich line for each type 2 point, and one component can look like that. But it's like when.
Yes. So if you look at each type 2 point, okay, locally, it's going to look at this global picture as well. So it has some fractal thing going on.
And is there some fractal dimension, Hausdorff dimension?
You can study Hausdorff dimension, and this has been done by Baker and their collaborator on their study. They did the potential theory on this Berkovich space, and in fact, you can study the dimension, the Hausdorff dimension of these spaces using potential theory. This is something that has been done, and you can define the capacity of sets. There's a lot of things you could say about them. Yeah. Okay, and as I said, it also has well, it has actually 2 matrix structure, but the one that is really interesting is in the rest of this presentation is the following. So because you have a real tree, so if you take, so here in this picture you have 2 points, x and y. The last point, rho, is thought as being the root of the tree here. So if you want to compute the distance between x and y, there is a unique point that is joining the path from infinity to x and the path from infinity to y, which is called x wedge y. Okay, and the distance between x and y is essentially the distance between x and x wedge y plus the distance between y and x wedge y. Okay, this is also related to the Gromov product. In fact, this distance is the distance that Gromov has defined for hyperbolic spaces, zero hyperbolic space. In fact, a real tree is also a Gromov zero hyperbolic space. And you take the log because, I mean, okay, you could define the distance without the log. Okay, you take the ratio of the diameters. But in fact, when you take the log, it's well suited for many reasons. One of them is, remember that the diameter is an element in PQ, P to the power Q. If you take the log, you get a rational number. It is also well suited when one is doing potential theory on Berkovich spaces. And it has a lot of similarity with the case of the log in the complex plane as well. So for these reasons and others as well, for the action of the group and getting isometric action, it's more interesting to consider this distance. Okay, so of course now we know the space, and to study the space, you could either study it from an analytic analysis approach. So you work on this space, you study measure on that space, you study functions on that space. Another approach, which is more well suited when one wants to study the non-commutative geometry that is in fact behind the picture here, is to study the action of a group on this space. And what is very interesting about the Berkovich line is that the automorphism group of this space is exactly PGL2CP. So PGL2CP, so it's the group of Mobius transformation. Okay, so AB plus AZ plus B over CZ plus D, where now A, B, C, and D are elements in CP. This PGL2CP, it acts on the Berkovich projective line. It acts by translations, and it acts by inversion. Okay, and in fact, translation and inversions are enough to understand the action of PGL2CP on this tree. So for instance, the action of PGL2CP is going to be transitive on the type 2 points, and the inversion will take you from the lower half plane to the upper half plane. Okay, it's going to inverse the radius when the radius is not non-zero, and when it's equal to 0, it actually sends you to a point at infinity. Okay, so as I said, it's a group of Mobius transformation. Of course, you require that the determinant AD minus BC is not 0. It's the automorphism group of P1 Berg CP. It acts isometrically not on the full P1, but on the hyperbolic space, so on the interior. But it's continuous on the full space. Very importantly, it preserves the type of a point. So if you act by a Mobius transformation, it's going to send a type 1 point to a type 1 point, so a point in the boundary to another point in the boundary, a branching point, a type 2 point to another type 2 point. And this is very interesting because if you think in terms of representation theory already, because the type 2 points are dense, you can study the representation by restricting the action of the group on the type 2 points. Okay, and by continuity, you can then look for continuous extensions of this representation to the full space. And why is this interesting to restrict to type 2 points? Well, the action is transitive on the type 2 points. So before diving into the representation theory, of course, you have the usual morphism of SL2CP into PGL2CP. which associate a matrix of determinant 1, an element of the Mobius transformation. Okay, so you can always assume that the determinant is equal to 1. And you can define a norm, which is the matrix norm in this p-adic sense, which is going to be the log of the maximum of the p-adic absolute value of A, B, C, and D. And of course, the kernel of this morphism is plus or minus identity. You have a Cartan decomposition of PGL2CP. So let me recall my notation. So OCP is the valuation ring, so the ring of integers, which is the set of elements in CP, the p-adic complex number with p-adic value less or equal than 1. And so you can Cartan decompose any element of SL2CP. So if you take gamma element in SL2, it can be written as M times A times N, where M and N are elements in SL2 OCP. There is a CP missing here, which is the ring of integer. And A is a diagonal matrix. Okay, with element. So it's sort of SVD decomposition, if you want, in this case. And the absolute value of lambda can be taken to be greater or equal than 1. Furthermore, the matrix norm of gamma is equal to the matrix norm of A, this diagonal matrix, which is equal to lambda. For instance, the Cartan decomposition of the translation. So you think that, for instance, think a translation acting on the Gauss point and sending the Gauss point, so the ball of center 0 and radius 1, to a ball of center B and radius absolute value of A. Then its Cartan decomposition is the following. And here, if you assume that this point stands below the root, then the absolute value of B times A is going to be less or equal than 1. So the matrix on the left is really an element of SL2O. And then the matrix norm of this translation is going to be equal to the absolute value of A. Okay, so now we can talk about representation theory of PGL2CP. So as I said, PGL2CP acts on the full Berkovich space, but and it also acts therefore on type 2 points, and it preserves the types. So you have an action of the group on type 2 to type 2, and these type 2 are dense. So you can restrict the action on type 2 points. And in fact, what it does is that it gives you what it does, because it signs type 2 point to type 2 points and the action is transitive, it's actually doing a permutation of the branching. Okay, so you get a faithful representation of PGL2CP into the very large group, but PGL2CP is already very large as a group. But you get a faithful representation in Sn, which is the group of all permutation of the set n, so the countable set of integers, as a closed subgroup. Okay, so what does it mean? This means that PGL2CP is something called an oligomorphic group. So what is an oligomorphic group? So first, let me say a few words. Yes, please.
When you talk about representation theory, what do you mean?
Yes.
What is the field of the vector space on which you represent your group?
So for now, I'm not talking about field here. What I'm saying is Sn has a representation in a Hilbert space. Okay, so Hilbert space representation, classical Hilbert space. So the field would be C. And in fact, by embedding PGL2CP in Sn, you get as well a representation of this group. Okay, so it's going to be classical representation space, but in infinite dimensional space, Hilbert spaces. That's what I'm going to say.
Just a naive question. Have you heard about the people who are working on representation theory of such a p-adic group, like someone like Vincent Fischer or some people like that? Have you heard about that?
Sorry, I didn't hear the last.
A French guy called Vincent Fischer.
Yes. Representation theory. So there's a lot. No, maybe I've encountered the name. I'm not sure now that you ask me. Of course, I mean, you have a lot of representation theory on p-adic in this p-adic context. A lot of work. I'm not sure if this is the one that you're mentioning, but maybe you can let me know. A lot of work has been done in the case of QP, for instance, right? So SL2QP, for instance, which acts on the Brad-Titz tree, which is a tree that is locally finite. Okay, you have a finite number of branches. And because it's locally finite, you have a lot of machinery that is already available. I mean, you have a classical theory that applies to this. You can define trace formulas. You can do all sorts of things on SL2QP. And this machinery is not available for PGL2CP because this is a non-locally compact group, which at first glance is frightening a little bit, because you're saying, okay, PGL2CP is already a huge group, but moreover, it's not locally compact. But there are some miracle that happens, in fact, in this case, that makes it a very interesting group to study. I'm going to mention some of them in a few minutes. But yeah, what I've seen is a lot of work done in representation theory for in the case of QP. But if you've seen something done in the case of CP or I should say non-locally compact field, I mean, you could send me some references. I'll be happy to look at them. So, is this answering your question?
Yeah, I will send you some.
Of course, please, thank you. So it makes PGL2CP an oligomorphic group. So oligo means few. Of few sorts, and morphic means patterns, if you want. So an automorphism group is oligomorphic if its action on n tuples has only finitely many orbits. So these groups have attracted a lot of interest in recent literature. Recently, Tsenkov proved a very interesting Peter-Veil analog, and this is what I'm mentioning. So you may think that PGL2CP is a group that will never have, a decomposition into unitary representation because of the fact that it's non-locally compact. But in fact, the miracle happens, and you have some sort of this statement. And a lot of works done on oligomorphic group is actually an extension of the study of SN, so the group of the permutation of the full set of integers, which is infinite dimensional. And a lot of work has been done by Lieberman in the approach. So Lieberman has an approach using Voinerman algebras and Voinerman theory. And then it has also been studied by Olshensky. So this is the Russian school. And there is a very thorough literature on representation theory of this infinite dimensional group using something called semi-group and something called also Olshensky pair, which is an extension of a Gelfand pair. And PGL2CP sits in this, so we can use this machinery at our advantage in that case. So let me cite the theorem of Tsenkov, which says that if G is an oligomorphic group, then there are only countably many irreducible representations of G, and every representation of G is a direct sum of irreducible representations. This is fantastic, okay? It means you have irreducible representation and you can decompose them. Of course, unfortunately, many of these irreducible representations are not finite dimensional, but still, we have them, we know that they exist, okay? So we'd like to study them. So we know that we have unitary representation, but what about more constructible representation? Can we get a hand on something that we can actually construct and compute? And the answer is yes. So first, I'm going to talk about, so all the representations that I'm going to talk about are going to be in Hilbert space. Okay, so over C, so nothing will be non-Archimedean in this Hilbert space, right? It's classical Hilbert space. So we can construct this Hilbert space. Since the Berkovich space is a real tree, there is immediately a canonical construction which associates a Hilbert space to an arbitrary real tree. So how do you do that? You declare a formal vector EXY for every vertices in the Berkovich tree, so X and Y. And then you assume that if you permute X and Y, you get minus the vector. And then the inner product between two of these vectors is going to be given by plus or minus the length of this of the intersection of the lines between X and Y and U and V. Plus or minus depending on the orientation of these lines. So you can give an orientation to every edge, and then you take this inner product with respect to this. So this gives you a Hilbert space associated to this Berkovich line. And you can define a one cocycle. So a cocycle map will be this gamma map from G to H that satisfies, well, it's 0 on the identity element, and it satisfies 2 will be the cocycle property. So here I'm assuming that I have a representation of my group into H, and then a one cocycle will satisfy gamma of GH will be this representation that I'm assuming that is given here, times gamma of H plus this translation gamma of G. And in the case of PGL2CP, the map gamma that to G associate the vector that is joining the root, which is denoted by zeta. So this is the Gauss root. Okay, so it's the point corresponding to the pole of center 0 and radius 1, and it's a root of the Berkovich tree. And so you consider this vector joining the root to G times the root. So imagine G is a translation or an inversion of the root. And so this vector, this association of G to this vector defines a one cocycle for PGL2CP. And in this theory, in fact, this one cocycle is, if one knows a little bit about a group representation for locally compact groups that admits a length function, then this will be the analog in the case of PGL2CP. So if you take the norm of this vector, or the norm squared, this will play the role of a length on the group. And of course, it has a fundamental importance on the representation theory of PGL2CP. So for every representation, pi, I can define something called an affine isometric action, which is the data of the representation and a one cocycle. And you can consider the set of all affine isometric action, and this gives you a transformation on the group. And you can define a representation, using this affine isometric action, you can define a representation. Okay, so this is also something that you can do using a one cocycle. Okay, you can define isometric action on Fock spaces. I'm not sure I will have time to talk a lot about this, but this is also something to keep in mind, that this one cocycle also gives you affine isometric action. We can compute this length function for PGL2CP using the Cartan decomposition. The length of gamma G squared is actually 2 log the absolute value of lambda, where lambda is the eigenvalue in the diagonal matrix in the Cartan decomposition. And here's, since my distance is defined using this log function, I get a rational number. Okay, and so this computation is very straightforward using the Cartan decomposition. And so you see that you have some arithmetic going on already just by studying this length function, because its image is in the rational numbers. So now we can find some something called spherical representations. So whenever you have a group that is acting transitively on a space, and here it's act transitively, sorry, on type 2 points, it's easy to get representations of such group. So for this, you can define a family of measures. So you have a classical measure on the Berkovich space that is invariant under PGL2CP because you have an isometric action on a compact metric space, Hausdorff metric space. So you can find an invariant measure, which we're going to call dx. And then using this measure, we can define a family of measures by declaring that the measure of g times dx, so this translation, is p to the power s over 2, the length of gamma times dx. Okay, so you twist the measures by this rational number to the power is. So this gives you quasi-invariant measures, family of measures, parameterized by s. Here s is a positive real number. And you can define a Hilbert space, HS, which are the functions on P1 CP that are square integrable with respect to these measures. And you can define unitary representations by taking the left representation, so by translation, and multiplying it by the Radon-Nikodym derivatives of these measures to the power 1/2 plus is. So the 1/2 is here to gives you a unitary representation with respect to this dx measure. So we get a family of unitary representation on all of these are spherical representation, which is to say that if you have a cyclic vector and you look at the state that is associated to this representation, you get exactly lambda g to the power is, which is a positive definite function, and it's actually the counterpart of the spherical representation that one gets in the case of SL2 QP. There are also other types of representation using this affine isometric action, which are related to the previous one, to the spherical one. So instead of considering the Berkovich space, you take the Berkovich space times the rational number, and you have the action of G on this space, where on the X you act by translation, and on the rational you translate by the length. Okay, so this gives you an action on P1 times Q. You put a measure on Q. You have to put some measures on Q here. So I'm putting this under the carpet, but it gives you an action on some L2 space on over P1 times Q. And I cannot resist to mention something, is that if you try to take the Fourier transform, okay, so a decomposition of this representation on the space of, so on the right-hand side, so the rational points, you get the Pontryagin dual of the rational, so which gives you the adels mod the rationals. So there is an adelic picture that is behind the scene here that is also very important. So this will be work that will be done in a full paper, hopefully, coming up in a couple of months, hopefully. Okay, so, and of course, using this, you can also define Fock space representations and all of this. I mean, I could spend more time dealing with representation, but I would like to mention in the few minutes that I have left, something else that one could also study about this Berkovich space is invariant measures. So invariant measures in the non-commutative worlds has another incarnation, actually a much bigger, much deeper, profound incarnation, which is KMS states and invariant measures. So let me briefly recall what a KMS states and a C-star dynamical system. So I told you about the action of PGL2CP onto the Berkovich space. So if you're able, I'm just saying if, I'm hiding some details, but if you're able to find a C-star algebra that is associated to PGL2CP, and this is not an easy task, okay? PGL2CP is non-locally compact, you don't have a Haar measure. Okay, so you have to do more work. But if somehow you have okay, you can say, okay, and that's what I'm going to talk about. You can consider, say, a discrete subgroup of PGL2CP. So, and say you have a C-star algebra, okay, associated to this group, and this group acts on the Berkovich space. So on the other commutative C-star algebra, which is a space of continuous function on the Berkovich space. So this defines a C-star dynamical system if you add to it a semi-group action. So from the reals to the automorphism group of this C-star algebra. And then states on this C-star algebra is an element on the dual that is positive on the self-adjoint element and which norm is equal to 1. You have a one-to-one characterization between GNS and representation through the GNS construction. Okay, so this is straightforward 101 construction in C-star algebra. And what is the KMS states? The KMS states is a particular state. It has some symmetry, additional symmetry. So a state in the C-star algebra satisfies this KMS condition, a Cobo-Martin-Schwinger condition, with respect to this automorphism group. So one has to think of sigma as being an action by, so you have an Hamiltonian on your algebra, and you take the exponential ITH, and this acts by conjugation on your algebra, and you can associate the KMS states to this if your states, so phi of AB, if you commute, you have this twist by sigma at I beta, so at time I beta. And if beta is different from 0, phi is a KMS beta state, then phi is sigma invariant. Okay, so you have an invariance under this action of sigma on your Berkovich space. And this can be related to invariant measures on P1CP. So why am I interested by this? Why is this important? Okay, so invariant measures are important when, for instance, in the classical space, okay, for instance, in the disk, okay, the classical disk, invariant measures play an important role, and they are produced by the Poisson kernel and the harmonic measures. Okay, this gives you invariant measures on the boundary that lives on the boundary on the disk, and they are the so-called Patterson-Sullivan measure. They are very important in many aspects of complex analytic spaces, also related to Hausdorff dimension and all computations of all sorts. And this Patterson-Sullivan measure is tightly related to something called the Busemann function, which is living on the boundary and which is defined by the log of the ratio of the Poisson kernel evaluated at y and x. Okay, and this produced the Patterson-Sullivan measure. And in fact, what is really interesting is that you can produce the same type of measures in the Berkovich context. So first of all, in the case of Berkovich space, you can extend the definition of the Busemann function. Sorry, there's a typo here. One should read a function without name. Using the definition of the metric on the Berkovich space. And it turns out that if you consider a group acting on this space, which has a finite dimension, there exists a unique measure that is the Patterson-Sullivan measure associated to this group action that lives on the boundary on the tree. Okay, but here you already have to be very careful about the group that you're choosing. Okay, already you have to put some restriction on it. Okay, which is to say that it has finite dimension. Okay, so it's and you have a measure that is quasi-conformal, quasi-conformal measure under the action of this group. Okay, and this is what you could do with the Berkovich space. So instead of considering the full PGL2 group, one restricts itself to the Schottky subgroup, which is essentially a discrete subgroup of PGL2CP. And you're choosing specifically a discrete subgroup because then you have a lot of machinery to prove existence of such measure. It is very restrictive, but nonetheless, a lot of the analytification from algebraic to the Berkovich analytic space comes under the action of a Schottky subgroup. And so you give this action on the Berkovich space. It defines a limit set that is on the boundary. And then using that, because now you have a discrete subgroup, you can take a covariant representation of the cross product. So this is a usual construction when one is interested in studying C-star dynamical system. So you consider the space of continuous function on your space and a group acting on them. And the interesting guy to consider here is the cross product between this C-star algebra of continuous function and the group action. What I'm morally, I mean, if you want an analogy here, if one doesn't really know about C-star algebra, what you're really doing is Fourier series, decomposition of Fourier series under the action of this group. And this Fourier series lives in this cross product here. And then you can define a one-parameter automorphism, okay, given a Hamiltonian on this space that acts on these Fourier series and twists them by p to the power it times the Busemann function. Okay, and look, this is very similar to the spherical representation when one is twisting by the length function gamma. Here, the length function on the boundary is taking the form of the Busemann function. Okay, and so you have this spherical representation showing up even in the case where you restrict it to a discrete subgroup of PGL2CP. And so one can define a KMS states, and there is a unique KMS states in this case. And this KMS states is exactly the Patterson-Sullivan measure on the Berkovich space associated to the action of gamma. And the Hamiltonian is exactly the Hamiltonian that acts on functions, and the eigenvalues is given by the length function. Yes, by the length function squared. Okay, and you can define also a self-adjoint square root D, which in the philosophy of non-commutative geometry is the Dirac operator in that case, which has eigenvalue given by exactly the square root of this length function. Okay, so you have already, even if you consider the case of a discrete subgroup, a lot of geometry showing up. Now, of course, this is not totally, we're not totally happy with this construction because we had to restrict to discrete subgroup. What about the full PGL2CP group? We believe, and this is what we're going to, we try to do in future works, is to consider, because we have them, we have the full representation theory of PGL2CP. What can we say about the full C-star algebra over PGL2CP? Okay, because PGL2CP is the real guy in the story here, more than just a Schottky subgroup. The long shot, okay, I cannot resist to maybe give you a bit of what we're trying to do here is sort of an adelic construction. If one knows about adelic decomposition, in the case of the reals, you can decompose using the rational p-adic rational numbers, and then if you put everything together, you have the adels. You have the Archimedean places, and then you have the non-Archimedean ones. Now, the long shot would be to do the same case in the complex p-adic work. But this is a story for another time. So thank you for listening to me. And if there is any additional question, I'll be happy to try to answer them.
Thank you. I have some questions.
Yes, please.
You should. Yeah, so my first question is on your last slide, we talk about self-adjoint operator D.
Yes. Yes.
Can you make a spectral triple with that?
Yes, in this case, yeah, that's a good question. So in this case, because we restricted to discrete Schottky subgroup, which are discrete group, it turns out that the spectral triple are nice enough. In fact, they are going to be some summability conditions. So you can say things about them. Now, if your question is about the full PGL2CP group, that's another story. It is true that you have a Fredon operator in the case of PGL2CP that is essentially the operator that, and this is also already present in Alan Cohn's work on the group F2, which also act on a tree, is a Fredon operator that takes a point and send you back to the root. Okay, what is fantastic about the Berkovich space is that you have a God-given canonical root, if you want, which is this Gauss point. And it allows you to define a Fredholm operator that takes you from any point on this tree back to the root. Now, in the case of, for instance, SL2QP, these Fredholm operators allow you to define spectral triples that are summable because QP is locally compact, and you have theory about that. You can relate this as well to amenability of such groups and something called Agerup property, which leads to summability of these Fredholm modules and Dirac operators. In PGL2CP, I don't know. In PGL2CP, we have unbounded Fredholm operators. What to do with them? Well, unbounded spectral triples, what to do with them is not clear yet. It's still work in progress.
And for this self-adjoint operator, for which it works, do you have an idea of what should be some, for example, the dimension spectrum or something like that? Is it related to observed dimension or something like that?
I don't know that. I'm not sure I can answer to that. What is interesting is that so first, I cannot answer your question. I'm not sure I know what the answer is, and I don't have a guess. What is interesting, though, is that the eigenvalues of these operators are rational numbers, which already gives you maybe some intuition of what the spectrum should look like. But for the Fredholm modules on the Berkovich space on the full PGL2CP, I want to be careful about what I'm going to say. I'm just going to say I don't know yet. But yeah, you may have some ideas.
And my last question is what about question related to bound-cone conjecture or something like that for such group?
Okay, well, it's funny you are asking that because we were talking about that with Masoud today at lunch. I mean, that's definitely something to explore here. I haven't dived into bound-cone conjecture in that context, to be honest. Maybe I don't know if Masoud is still on in the Zoom. Maybe he'll be able to say more things about that. But definitely, I mean, there is a lot of interesting structure showing up, and one question would be, what about the bound-cone question? And that's definitely something we would like to address in the future. But yeah, it's we don't know.
We check this. Yeah, he's online. If you want to, if Masoud want to say something, he can. Otherwise, no. Okay, let's stop here. Thank you very much.
Thank you. So I'll stop sharing.
Thank you. That's really, really nice. Really nice. Very interesting.
Thank you. Thank you very much. Thank you for listening. I see there's quite a lot of people.
Yeah, we had 20 people online and 10 people in the room. Okay.